Hello everybody, Root Beer here, and we have made it at last to the end of our 2012 MMC, Manitoba Mathematics Competition. Maybe you're just joining me for the last question, in which case you can download a copy of the contest by clicking one of the links below. But we're here, we're at the end, it's question number 10, let's have a look. Okay, and if you are just joining me, pause the video, try the question for yourself, and if you're curious at all about any of the other questions, by all means go back and watch those videos. 10. A square of area 1 is divided into 3 rectangles which are geometrically similar. They have the same ratio of long to short sides. We know what similar is. Okay. But no two of which are congruent. So they're not exactly the same rectangles, but they all look like they have the same proportions. Okay. Write A, B, and C for the areas of the rectangles ordered from largest to smallest. So A is the largest. B is definitely smaller than A. C is definitely smaller than B. Okay. Prove that AC squared is equal to B to the 5. Okay. So, one wonders, is this some geometric relationship that is just true when you divide a square up in these particular ways? Or is there just one particular way to cut a square in this manner into the 3 rectangles? I'm inclined to believe it's the latter, just because, and this is just from experience, you'll notice here we've got a b to the 5. Fifth powers don't usually, at least in my experience, pop up when you're talking about areas and two-dimensional things. Like the square is fine, and if this were a 4th power, maybe. 6th power, maybe. But 5th power, that seems bizarrely out of place. I could be wrong. Maybe I'm about to discover something new. Heck, maybe I might get stuck on the question altogether. But I'm of the opinion, just because of that 5 there, that there will likely be only one way to divide the square into 3 rectangles that are similar but not congruent. Okay? So if that's my feeling, that's what I'm going to try and show first. And then I'll be able to calculate these side lengths and these areas, hopefully, and be able to demonstrate and just say, yep, this result is true. That said, maybe as I'm trying to show that the division is unique, I will find that, oh, no, there's a lot of different ways to do it, but they all have this thing in common, and I can use this thing to show that AC squared is equal to B to the 5. Okay? So, I'm going to grab our pen, we're going to grab some paper, and we're going to go at it. Now, dividing this thing in a square, just going to explore just a little bit here. If I were to divide it up, I could do sort of this, and then sort of like reverse Fibonacci, we would, get something like this, and then this one here is a smaller version of this guy here, and then this one is a smaller version of those two, but put on a bit of a slant. That's one way to do it. I mean, obviously you can just chop it up into these 3, but they're all congruent, so that's no good. Don't want that. What else could we do? We could get one like that, and another slant, so him rotated and shrunk, but that'd be the same as this one here, unless these were both the rotated and shrunk, but I guess then they'd both be congruent, so that's not going to work. Huh. Okay. I'd need to be able to show it's unique, so we got to start. I think we can start with a pigeonhole principle, so let's see if this works. There are 4 sides to a square. No, we don't want to say 4 sides if we want to do pigeonhole principle. I was going to say there are 4 sides, so there's got to be one, and only 3 rectangles, so there's got to be one that sort of spans a whole side. I don't think that's necessarily true. There are 4 corners. And there are 3 rectangles. So there must be at least one rectangle It must be that containing at least 2 of the square's corners. Alright, I mean, this guy here, he's got these 2, and this guy down here, he's got these 2, and this guy's got these 2, and this guy's got these 2. There's no way to do it. You have 4 things, 3 buckets to put them in. 1 bucket's going to have at least 2 things. Okay. So, if such a rectangle had 3 or more corners of the square, then it would have all 4. Alright, I can't take this this square here and have these 3 be part of a rectangle and not have this one down here. He comes by default because then the square would be just be one big rectangle and there wouldn't be any others. Okay, so rectangles have 0, 1, or 2 corners in common with the square. Okay, so that's logically true. I'm going to say, suppose a rectangle has 2 opposite corners. This should be ridiculous. So it must have the other 2. And so be the whole square. So that's not allowed. We don't want that. So a rectangle with 2 corners must have these corners be adjacent. Alright, so thus such a rectangle must contain a side. Okay. So where does this get us? So if we've got our big square, we say maybe this is the side. We have a rectangle. He's got to have this. Now there might be another rectangle that has this side. Yeah. So what could we have? So what possibilities are there? Okay. We could have rectangle 1, rectangle 2, rectangle 3, and we could have 2 corners, no corners. We could have 2 corners, 1 corner, 1 corner. And I think that's it. So we have sort of situation 1 and situation 2. Now I think these can be broken down into smaller cases. So for this one we'd have we could have all 3 of them congruent. Or what could we do? We could have the bottom one and then the top one here be congruent but sort of the other way. So let's say we have 1 and x. And then we can have this guy have this. My picture is not doing this justice. So we have 1x, 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 but we've got congruency here. Okay, all of them are congruent. Or we could have 1 and x, and then we could have the big one down here. He wouldn't be 1 and x, he would be the one would be where the x is. It'd be rotated, and all the sides would be multiplied by 1 over x, I guess. But then this guy here, he's got to have a side. He's stuck. He's congruent to one of them. So that doesn't work. We could probably write this up a little neater, but the point is either the two that are on the square's sides are congruent, or the middle one now I want to say this better because I feel like we should properly justify this before we move on. The middle rectangle has a side of length 1 as well, by default. And so it's another pigeonhole here. There's only 2 ways to have length 1 and the same ratio. So you have 1 and x, or you could have 1 and 1 over x. These are both x to 1 sort of squares. So we've got 3 rectangles, but only 2 ways to do it with a side length of 1, so there must be a congruency. So that leaves this other situation. We have 1 rectangle that's on a side, and then the other 2, they just are stuck in the opposite corners. So situation 2, what are we looking at? We have the big guy, and he's saying, well, the x was really serving us well. And then we have sort of some division down here. But they both have this same length here at 1 minus x. So we could say something like, let not one square, one rectangle. Have dimensions 1 and x. So this means other two, the smaller ones, have rectangles have 1 minus x as a common side length. But as I just noted, if I give you a specific side length and a ratio, which we've got 1 to x, that's a ratio of the sides, they all have to be similar rectangles, we're fine. And I give you a side length like 2, you can either have 2 to 2x or 2 to 2 over x. And that's the only way to do it. Those are the only ways you can have the same ratio, have one of those side lengths fixed, and still be similar. So if that's the case, then we really do just have one. You can either have both of them. If they're not going to be congruent, then one of them has to be sort of the 1 to x, and then the other one has to be the 1 to 1 over x, that sort of thing. So there really is just going to be this one way to do it. And I think once we have that, we can solve for, I don't know, x, and then we're all set there. So as we just noted, with the same ratio of sides and a fixed length, there are only two ways to create satisfactory rectangles. Okay. So we would have sort of 1 minus x and then x, 1 minus x. And then the other one where the 1 minus x is where the x is. So then it would be 1 minus x over x. We must have one of each, so as not to have congruency. So we're looking at we get 1 minus x here, and then we'll get let's say x, 1 minus x here, and 1 minus x over x here. And these two can't be the same length, so we can't have like a half here. But I don't think we have to worry about that. I think it'll be fine. So there's only one option, although I admit I think we might get like a quadratic in x, in which case then there is more than one possible x to solve for. And then that might give us more possibilities. So I might have been wrong. I might be wrong. There might be other ways to do this, but this is sort of the only setup we can have. There might be a couple x's that will give us a square, a 1 by 1 square here. But I think those x's will all be related in some way to give the AC squared equals b to the 5. Okay, so I was half right, half wrong, I guess. I was correct in that there's sort of only one way to do this, but we might be able to fiddle with the x's or something like that. In which case, then there's technically more ways, but the essence of the ratios is all still the same, I guess. Oh well. So what can we see? We can see that 1 is the same as 1 minus x over x plus x1 minus x. So I guess multiply through by x, we'll get x is the same as 1 minus x plus x squared 1 minus x. I'll expand that out. So we had x is 1 minus x plus x squared minus x cubed. So 0 is 1 minus 2x, so it's a cube. Interesting. And I think that's what we wanted, right? Yeah, plus x squared minus x cubed. So, I wasn't expecting a cubic. Can we solve that? Are there any stupid vacuous solutions? 0, no. 1, no. A half, maybe? No. See, I don't have a cubic formula memorized, and even if I did, I probably shouldn't be using that. So I don't actually see a value of x. It's not the best thing, but maybe we don't need it. Maybe there's something about this particular equation that works. I'm noticing we got x cubed here, not helpful, but this right here is 1 minus x squared. That might be useful. What do we got? Well, what did they actually tell us to do? We had an A, a B, and a C. So we had 1 minus x. We had x minus x squared here, and then we had 1 minus x all over x. We had 1 and x. So this guy's the big one. Is there a way to tell who's the small one? X has got to be less than 1. So if we, so this is 1 minus x divided by x, and this is 1 minus x times x. So since x is less than 1, this is smaller. So then this one's got to be the bigger one, and this one's got to be the smallest. So, area of A is 1 times x, which is just x. Area of B and area of C, these are going to be a little more complicated. Area B is 1 minus x over x. So 1 minus x cubed, or sorry, squared, which we have over here, over x. And the area of C is 1 minus x, 1 minus x, which is x, 1 minus x squared. Okay. So AC is just x squared 1 minus x, all squared. And B is the same thing, but with, well, very similar, but over x. So we want AC squared. Well, that's going to be x to the 4, 1 minus x to the 4. And B to the 5 is 1 minus x to the 10 all over x to the 5. We want to show that this is somehow true. Suppose it were. Suppose we did have AC squared is equal to B to the 5. Then we'd have x to the 4 is 1 minus x all to the 4, which is 1 minus x all to the 10. I'm seeing some similar numbers here. So we can get x to the 9 divided by x minus, or 1 minus x to the 4. So that's 1 minus x all to the 6. And then cube root it, and we get an x cubed. Hey, we got an x cubed over here. And then we cube rooted, so 1 minus x squared. Nifty. Okay. So by our construction, 0 is 1 minus 2x plus x squared minus x to the 3. Or rather, x to the 3 is 1 minus 2x plus x squared, which is equal to 1 minus x all squared. And since that's true, then we can cube both sides. We get to the power of 6. And that's x to the 5, x to the 4. And that's 1 minus x to the 10 over 1 minus x to the 4. So now we just move everything over x to the 5. But this is a c squared, and this is b to the 5. Okay. And that's all we had to do. That's all we had to show, right? Prove that this. Okay. So that wasn't that bad. It was interesting, an interesting mix, I think, there of we had some pigeonhole, and I don't know what their solution was. I don't know if this was the fastest way to do it, or if they went into more detail, less detail. We had some pigeonhole with those corners. We ruled some things out, said you got to have something that's got a line in common. I could have probably done that a little more detailed or explained it a little better, but I think what I did was fine. Probably should have said pigeonhole principle at some point in there. That would have been a good thing to do. And then what else did we do? So we had pigeonhole principle, and once we had that, gosh, we basically, it reduced down to a single geometric result there. Or, sorry, a sort of a family of possible ways to arrange these rectangles. I'd be interested to see that cubic. How many solutions for x does it have? Because it feels like there should just be one. Just because this sort of, once you have that relationship of rectangles, there should just sort of be the one solution for x there. That's something I'll do afterwards. I am of the opinion there's just one real solution for x. It's probably two complex solutions. But once we had that, we had the relationship with the x's. We didn't actually need to solve them. I don't think I could have. Nothing was coming to mind. Certainly no integers and no obvious fractions there. But once we had that relationship, then we said, okay, well, here are all the side lengths. We've worked out all the side lengths in terms of x. We can get a, we can get c, we can get b, and actually it was pretty quick from there. It's pretty quick. So the bulk of the question was sort of pigeonhole and ruling out different cases and saying these three rectangles, they gotta look like this. That's about it. I'd be interested to see how many ways you can do three rectangles. If we take out the no two congruent, how many possibilities are there out there? And that would be setting up each of those cases, solving for various x's, but that's something I'll do on my own in private. Not a bad question 10. I liked it. I was able to sink my teeth into it right away, but there we go. That concludes the 2012 MMC, the Manitoba Math Contest. I liked it. Hopefully you guys did too. And if you're going to watch the next one, I'll be going through the 2013, or maybe you'll just browse around my channel for some other contests, whatever you want to do. I'll see you guys in the next video, and as always, thank you so much for watching.